So I've cleaned things up a little bit and relocated joint B over here. You don't have to do that, right? You can just continue with your work. I just needed the space. So what I also did when I reproduced B here is I put all of the forces that I calculated in the correct direction. So notice how I'm showing 30 as a compressive force. If I still kept it as a tensile force, I'd have to put a magnitude of minus 30, okay? All right, so I'm going to move on to D. I can move on to any joint, but I like D because why not? I scooped out D basically between all the inflection points. So I cut at 2, 4, and 3. Now, all I have to do is build the free body diagram and see if I can figure out all the interior axial and shear forces. I put on also the dimensions to make sure that it works out. First, I'm going to start with the forces here at 2 because I've already calculated them. Now, because I've already calculated them, I can just put them here. But I have to do it properly as forces. So I have to be careful about the direction. 30 is a compressive force. That means 30 must be shown as a compressive force. Just like that. 6 is a shear force that's trying to turn this end clockwise. Okay? Sorry, counterclockwise. So 6 is trying to turn this end counterclockwise. 6 here must turn this end counterclockwise. Okay? So it may look at first glance that these are opposite directions of that. I guess they are because they have to balance out, but this is the same shear as that because it's causing the same effect on that end and this end. This is the same axial force as that because it's causing the same effect, compression, at this end and that end. Make sense? Let's fill in the rest. Here, we know the shear force already. We calculated it earlier on. Right here, it's 20. And I don't know what direction the axial force is in. So I'm going to guess it nothing for now. And then here we have a y force and an x force. We can now be clever about this x force. Can we figure it out already without having to do some of the forces in the x direction? So look at this. 30 this way, 20 that way. What is this unknown to maintain equilibrium? It has to be 10 that way. So this axial force in this beam is 10 compression. Okay, so then I'm just going to guess, I don't know, these two axial forces in opposite direction, up and down. I don't know what they are, but our results will tell us. This here is 3y, right there, and this here is 4y. And I think the most efficient way to obtain one of these two is to do a sum of the moments somewhere. I choose to do, and that's my choice, yours can be different, a sum of the moments right at this inflection point 3. With counterclockwise being positive. So if I do a sum of the moments here, I have to figure out the moments caused by these 4 forces. These two have the same distance, 1.5. This one is causing a counterclockwise moment, counterclockwise, so I can just subtract the two properly. Okay, as such. Or you can just write it out. Then the moment caused by 6 is going to be 6 times a distance of 2.5. And this moment is positive, like that. And lastly, the moment caused by 4y. It's going to be 4y, a vertical force, times a horizontal distance of 2.5. And this moment is positive. Okay? So now I'm just going to solve for 4y. That's the shear in this beam at 4. If I do things correctly, it should come out to be 6. We get this as 6 kilonewtons. All right. Because it's a positive value, it also tells me that I have a shear going like this. Now, let's get back to this for a second. Remember how I showed the shear over here looking like this? It's because this is what it looks like in here at 4. Let's look at 2 for a second. The shear at 2 looks like this on this end and this on that end. That's why I showed it the way I did in part 1 of the video. So go check that out. Okay? All right. So if we know that 4y is 6, what is the value of 3y? Right, is 0. If this force is 6 down, that's 6 up. This must be 0. It's the only way you maintain equilibrium in the y direction. Okay? We're done with D. Okay? This is perfect. So now I think the next one we'll move on is G. So what I'm going to do is I'm maybe going to relocate this over here as follows. And erase this so that I have enough space to do G. Now G is going to be very interesting because it's going to be a check. I'm going to reproduce G here. And G kind of looks like a 7 almost. Where this distance is 1.5. This distance is 2.5. And now I'm going to show the known and unknown forces on it. Ready? We know the forces here at inflection point 4. We calculated them here. So that means we have to show the correct magnitude and direction here properly. So if this is a 10 compression, we have to show it as 10 compression there too. And if here we have a 6 shear force that is trying to cause a counterclockwise rotation, here we need the same thing. Right? You see how this 6 and that 6 cause counterclockwise rotations, right? Regardless of what end you're looking at from. Okay, now here, we're going to put in the known shear force. We know that already. We calculated it in our first 2 steps. This here is 10. Now, is that good? Yes. Look at this. They balance out. That's a first hint that it looks like we're doing things correctly. Second, we need an axial force right there, right? So this is going to be, there's going to be an axial force there. Can we already figure out what that is? Yes. We have an axial force going down, must be balanced out by an axial force going up, 6. That tells us that this column is in compression. Are we done? No. We've done X forces, we've done Y forces. The only way to ensure we've done things correctly is also doing a sum of the moments with respect to any location to make sure we get 0 equals to 0. If you don't do that, although it's likely that this is done correctly, you're going to run into a problem. That one time you make a mistake, your moments don't balance out to 0. However, I want to acknowledge this. That's great to say if you're doing this as an assignment or you're doing it as a project at the office. You have the time to check and fix your mistake. if this is a test, if you're doing this in the middle of a test, which is not real life, right? And you're timed, and you find that the moment is not zero, you don't get 0 equals to 0, continue, okay? You don't have time to check. That's why tests are not real life, okay? They're purely fictional. Okay, so I'm going to check just to make sure it's a moment. I have the time, and so do you. So sum of the moments equals to 0 at any location. I'm going to pick, I don't know, I can pick any location. How about we do here? So that's inflection point 4. So that means that these two forces do not contribute to moments with respect to 4, only these two forces. So what do we get? We get that 6, a vertical force times a horizontal distance of 2.5, and 10, a horizontal force times a vertical distance of 1.5, but that's a negative moment, okay? It's the opposite direction of that. Okay? And again, this is 0, right? Because we want the sum of the moments equals to 0. What do we get when we do that? We get 0. So that gives me confidence that so far, for the top story, for the roof, I've done things correctly. Okay? I'm going to clean things up, and then we're going to move on to the support reactions. We'll do that super quickly and wrap up the question. Find the link to the next video in the description below.